record button and get this up real quick. That's fine right there. All right, so I sent you a video on NMR, and there's some basic things that we need to know about NMR. Basically, it's going to tell us four main things about any molecule. Excuse me. All right, so before we even jump into that, there are multiple types of NMR that you can do, right? You can do proton NMR, which is what we're going to be talking about. That only looks at hydrogens. You can do carbon NMR that only looks at carbon. You can do fluorine NMR that only looks at fluorine. You can do phosphorus NMR. So there are multiple types of NMR spectroscopy. You do them all in the same instrument. You just change the probe in the instrument or change the settings in the instrument. All right. So today we're only talking about proton NMR, which is, you'll see it dictated or indicated like this, right? H1 NMR, right? That's what that means. The 1H NMR is proton NMR. So it'll tell you the number of non-equivalent hydrogens. That's the first thing. We're going to talk about all of that. So don't panic about not being able to get that down right away. It's going to tell you where they're located, right? Whether they are in electron-rich or in electron-poor environments. It's going to tell you how many of each type of hydrogen is present, and it's going to tell you the structure. It'll help you to determine the structure, tell you what's close by those other molecules. I mean, those other hydrogens. So that's where the splitting pattern comes in. So all of this we're going to talk about. All right. All right. Let me get this off the screen right quick, and then we'll keep rolling. All right. So as far as where hydrogens are located or the chemical environment, it can be upfield or it can be downfield, and this is all relative. Downfield is relative. Upfield is relative. So when we say something is downfield, that means it's in an electron poor environment. But downfield could be going from 5 to 5.1. I mean, it's that subtle. So it's not going to be a big difference. But downfield just means that it's further towards 10. Upfield means it's further towards 0. And then you have upfield is electron rich. Downfield, if you put an electron withdrawing group around a proton, it's going to move the shift downfield. That's called deshielding, right? All right. So let's look at some more information about NMR, right? NMR is short for nuclear magnetic resonance. It deals with the nucleus of an atom, and every nucleus has its own magnetic field. So there's a pre-existing magnetic field, and then the NMR instrument itself is just a giant superconducting magnet, right? So you put the molecule. Well, I'll show you how to do it. And some of us have already done NMR because of lab, so that's a good thing, right? What it tells us is the carbon-hydrogen framework of any molecule, right? And then the scale is from 0 to 10 parts per million, and then everything is expressed relative to TMS, which always shows up as 0. All right, so you've seen the instrument before. You dissolve up your sample in an NMR tube, the little tube shown here. That tube, you drop it down into, well, you don't drop it in the instrument, but you insert it. It is inserted into the instrument, and then the instrument uses radio frequency energy, right, to irradiate the sample. All right, so I think I've talked about this before, so I'll just run through this, and then we're going to jump right into some examples. All right, so you put your sample into the magnetic field. Remember, every nucleus has its own magnetic field. So when you put in the sample, right, all of your all of your nuclei are precessing on their own, spin. It's just random. Put them into the magnetic field, and then some line up with it, some line up against it. And then the purpose of the radiation is to get the ones that are lined up against the field to line up with the field. All right. And so when you pulse it, right, it causes those proton nuclei that are against the field, they line up with the field. So that's what this is showing here. But then in between pulses, those nuclei relax back, right? And so when that happens, it gives off energy, and then that energy is picked up in what's called a FID, free induction decay, right? And then you do a Fourier transform, which converts this from time, from a frequency into parts per million, and that's how you get a readable spectrum. All right, any questions? All right, so let's go back to here. I want to ask a question. How many signals are in this spectrum? Not lines, because some signals are one line, some are two lines, some are multiple lines. But how many signals are there? Five. One here. Excuse my crap. I'm doing this with a mouse, so it's kind of crappy. What you doing? What charger? It's right there. All right. So we got 5 signals here. Are you following that? And so when we talk about the number of signals, that corresponds to the number of hydrogens that are what we call non-equivalent, right? So over here, we have a set of hydrogens here. We got 2 hydrogens on this carbon, 1 here, and then these 2 CH3s are different, right? So that's where my 5 signals are coming from in this spectrum, right? Because I got 5 types of hydrogens on this molecule, all right? Is that making sense? Because that's going to really, you got that concept has got to be, you got to grab that before we move on to something else. Is anybody not seeing what I'm saying?
Dr. Russell,
Go ahead.
can you explain that one more time?
Yeah. So if we're doing proton NMR, right, where we're only looking at hydrogen nuclei, we don't care about any other atoms. Every hydrogen on a molecule that's different, we call them non-equivalent, right? And so let me make this example even, or try to make it plainer. So here, right, you got 2 hydrogens on this. You have 2 hydrogens here, right? One here. It's going to be ugly because I'm using my mouse. And one here. Is that right? So, but these 2, because they're on the same atom and because there's nothing around them to differentiate them, they are what we call equivalent. That means they're going to show up under the same signal, right? But they're going to give a signal in the NMR. So that's these hydrogens are responsible for one of the signals down here. And then the CH3 hydrogens right here, those are going to be responsible for one of your signals. And then the hydrogen here on the double bond, that's going to be, excuse me, responsible for a signal. And then the 2 CH3s are different. They're not equivalent. Even though they're both CH3s, they're not equivalent. And so each one of these is going to give its own signal, right? And so you have a total of 5 different types of hydrogens present. So that means you're going to get 5 signals.
Okay, that makes sense.
Okay. All right, great. All right. Any other questions? And we can even talk from this example about where these hydrogens show up and everything, but I want to go back. I want to talk about some other examples before we do that. But we're going to come back to this example and we'll probably close the class out with it to see if we actually are understanding what's going on. All right. Let me get this erased. All right. So you saw in the video Monday ethyl acetate, So now we're going to talk about proton equivalents or non-equivalents. So at the Aztec, you can see I got three different types of hydrogens highlighted. That should equate to 3 signals. Am I right?
Yes.
All right. So you should see 3 signals. So in the NMR spectrum, you can see that there are indeed 3 signals here that correspond to the 3 different types of protons. Now the question is, well, there are 3 hydrogens here, right? Why is it that these 3 don't give 3 different signals? Well, these 3 are equivalent to each other, right? But they're not equivalent to the hydrogens on this carbon or the hydrogens on this carbon. And so therefore the equivalent hydrogens are all going to show up under the same signal, right? The same with these 2 hydrogens. They are equivalent to each other, but they're not equivalent to the blue or the red. And so these are going to show up under the same signal, right? And then the blue hydrogens, there are 3 hydrogens on this carbon. They're all equivalent to each other, but they're not going to show up, or they're not going to show up under different signals. They'll all be under the same signal. Yes or no?
Yeah.
All right. All right. So the way that you test for equivalence, let's say I have this CH3 here, and I want to find out if it's equivalent to the hydrogens on this CH3. The way I do that is to take one of those hydrogens off. I got to go back to this pen. Go back. So I take one of those off and I put another atom on. So let's say I put a chlorine on. That's terrible. This reminds me of when I first started making videos. I didn't have an iPad. I was using a bamboo pad. That thing was horrible. Okay, so I put a chlorine here, right? And if I want to compare it to the red hydrogens, because that's a CH3 too, and it's a common misconception that just because it's a CH3, then it should be equivalent to any CH3. So if I want to compare it, what I'll do is put a chlorine on the other atom and take one of those hydrogens off. All right, so I put a chlorine here. Now, if I compare these two, are they the same molecule? Do I get the same molecule?
No.
No. If I were to name it, it would be 2 totally different isomers, right? And so that's how I test to see if a hydrogen is equivalent. I simply compare the 2 carbons where those hydrogens are located. I swap out one hydrogen with another atom. It doesn't have to be chlorine. It can be anything. If I get 2 different isomers, then they're not equivalent. If I get the same thing, then they are. By the same token, if I swap either one of these out with chlorine, would that give me something different? Either of the pink hydrogens?
No.
No, it would give me this exact same isomer both times, so it wouldn't matter, right? So that's how we know they're equivalent. And if I swapped out this with a chlorine and this with a chlorine and compared them, would I get the same thing or would I get 2 different things?
2 different things.
Right. So that's how we test for equivalence, right? But normally you won't have to do that, because if a molecule is not symmetrical, then you're not going to have you're not going to have any equivalent protons if it's not symmetrical. All right. So this just talks about it. So if protons are equivalent, we call them homotopic. If they're non-equivalent, we call them heterotopic, right? That's the takeaway from this particular slide, because we've already talked about how to test for equivalence or non-equivalence, right? So homotopic means they're equivalent. Heterotopic means they're not equivalent. All right. Any questions before we move to the next slide?